So, welcome to the first in this session of videos that has to do with the mole and molar quantities and things like that. Quantitative chemistry. It's kind of our first dip into um, analyzing chemical compounds in terms of the quantities of atoms that are present, the quantities of different elements that are there, and being able to do things like determine the formula of a substance based on lab data. That's kind of all places that we will go in this particular chapter. So one of the things I want to point out about this chapter is that as you are taking notes on this video or whatever, two things to have. Make sure you've got your calculator present. And then the other thing you probably want to have is the periodic table, right? Handy dandy periodic table from somewhere. It's most effective for you if you follow along and try to kind of attempt the math problems as I'm doing them. It definitely helps. Like if I introduce a math problem, hit pause, see if you can kind of work it out. And kind of make an attack at it, and then kind of hit play and see if I go the same direction that you were thinking of. Again, if you don't have a lot of background in this material and you're seeing it for the first time, obviously that's totally fine. You can just kind of sit back and listen. The other thing to keep in mind is that as you're taking notes on these videos, make sure that you're doing annotated notes. In other words, when you are creating your notes and you put a math example in your notes, make sure that you're labeling each step. Like here's step 1 is converting grams to moles. Here's step 2 is, moles to moles or whatever the Avogadro's number step or whatever is, but label the names of the steps. Don't just do the math on there. Leave yourself a note where those numbers came from or what those numbers mean. That's actually how to make these videos much more useful for you and how to make your notes much more useful for you. It's called following the line of logic. And that's that whole idea of, what are the steps and why are those steps? How do they follow? And it's one thing to kind of be in the moment and you're listening and it kind of makes sense. But then when you look back at it later, you know how it is. You look at your math, you're like, where the hell did that number come from? You're leaving yourself that map, that mental map of where that information is coming from and why it was relevant. So just a hint to help you kind of make a little bit more use out of this time. So this particular first video is just kind of about the molar mass. It'll be a fairly short one here. But again, the whole idea of what Avogadro's number is it has to do with the number of atoms that's found in a particular set quantity of a material. So Avogadro's that goofy looking dude on the left, like something looks wrong with that guy, but that's Avogadro himself. By the way, he didn't actually come up with the number. He just kind of came up with the concept. He was studying gases and looking at the way that gases interact and kind of came up with that idea that there had to be some sort of an equal number of particles that were interacting. And so him thinking quantitatively is really why we honor him by calling that number after him. It's like I said, it's not that he came up with a number, but that idea that chemistry was happening at the atom to atom level, that there had to be something going on quantitative below the level that we see it. That's really what the key is about the mole. And that's why chemists always kind of focus so much on this concept of the mole, because it's the concept that allows us to translate, I guess, between what's happening at the atom to atom interaction between bonds forming, rearranging, and interacting versus the bulk level macroscopic stuff that we observe. So when we see a precipitate form, or we see a temperature change, or we see gas bubbles form, that's bulk level, macroscopic at our size. And that's the result of millions of individual atomic level interactions that are happening. And the concept of the mole is what really allows us to kind of go back and forth between those two. So kind of like when you're talking about, the concept of how many atoms are interacting here, a lot of times I don't really care the actual number of atoms. What I really care about is knowing that I have these set case quantities, so to speak, easy to use values that allow us to sort of decode between the microscopic and the macroscopic. So when we are talking about the mole, an important thing to realize is that the mole is just a number. It's very much like a dozen, right? If I say we've got a dozen something, how much does a dozen weigh? Well, you'd need to know what that dozen was. Do we have a dozen cats? Do we have a dozen dogs? Do we have a dozen calculators? Do we have a dozen atoms, dozen human beings? A dozen's just a number. Well, a mole is also just a number. It just happens to be quite a bit bigger of a number because the numbers of things that we're counting are so much smaller. Again, we're talking about atoms, which are so tiny that we need a really huge value of them, a huge pile of them in a sense, to be able to see them at our macroscopic level. So between these two things, we have these interactions. There's two little conversions that we use regularly to allow us to sort of translate between these two things. So first of all, we have the atoms to moles interactions. This one right here. This is called Avogadro's number. And again, Avogadro's number is 6.022 times 10 to the 23rd items, whatever those things are. Usually those items are atoms, but they could also be molecules if we're doing that. But that equals 1 mole. Just like we say 12 cookies equals a dozen, well, 6.022 times 10 to the 23rd items equals a mole. The other thing that's really, really powerful about the moles concept is that we can also do this conversion, which is moles to mass. And this is called the molar mass quantity. This is actually what we see on the periodic table. And so molar masses are much more valuable for us to be able to say, hey, we're predicting how much quantity of atoms that we have present in this sample of salt, for example, because we know that we can kind of convert it from grams to moles. So that's the key kind of powerful thing about that. With all of this is that concept underneath of that idea of counting by weighing. And that's really important for us, that rather than trying to count individual atoms, we can group them together as a mole. And if I know how much that mole that weighs, then I know how many atoms are present in there. So using this concept again is that idea of molar mass. Now, again, molar mass is what's actually present on the periodic table. So if we talk about lithium and I want to know what the molar mass of lithium is, all I got to do is get out my periodic table, find the element lithium, there it is right there. And this little number down at the bottom can be interpreted two different ways. That number is 6.94. We could either say 6.94 atomic mass units equals 1 atom of lithium, but nobody cares about 1 atom of lithium. Who needs 1 atom of lithium? Like, really? Or we can say it more usefully, 6.94 grams of lithium equals 1 mole of lithium atoms. So again, this is a much bigger pile, 6.022 times 10 to the 23rd atoms of lithium, but 1 mole of lithium weighs that mass in grams. So that allows us to do a much more useful set of conversions. So if I want to know how many atoms are in 12.72 grams of lithium, I would start with my wonder fraction, 12.72 grams of lithium. I would do my big wonder fraction line. There's my per line. Again, follow the units. I need grams to cancel out. So I'm going to put grams down here. So now when we've got grams, the only thing I can do is do a grams to moles conversion. This is one of our conversions that we have, MOL. And I know that by definition, 1 mole of lithium weighs its atomic mass in grams, which is 6.94 grams of lithium. Now that doesn't give me the number of atoms. So notice how the question asks number of atoms. But now I'm in moles and I know how many atoms are in a mole. So I can set this up again, one more step. 1 mole of lithium equals Avogadro's number, 6.022 times 10 to the 23rd atoms of lithium in this case, and atoms of whatever it is, but that's how we would do that final conversion. And so at this point in time, you can just do the calculator and figure out what your value is. It would be 12.72, again, multiply across the top, divide by everything that's on the bottom, so 12.72 divided or times 6.022 times 10 to the 23rd. Remember how to use your calculator? I'll remind you in class tomorrow how to do that, but use your calculator appropriately. And then divided by 6.94. And we get, it's got to be some crazy big number since we're talking about numbers of atoms. 1.103744 something, something, something. And then it says E24. That's kind of what my calculator says on there. So how do I interpret that? Again, that's my calculator output value. How do I interpret that? Sig figs, units, and then this E part. So remember on your calculator, E means times 10 to the. So this is my calculator telling me this is in scientific notation. So 4 sig figs and 4 molar masses, a couple of general rules. Again, sig figs, always look at your original problem. 4 sig figs is what we've got to work with. Never look in the conversions, or I always say almost rarely, but basically never look in the conversions. When we are doing molar masses, by the way, we will always use 2 decimal places. That's a convention that's very commonly used. So yeah, I know this one technically has 3 sig figs, but again, we're not going to worry about that too much. Look at your original problem. 4 sig figs in my original problem means I want 4 sig figs in my answer. It's a great rule to go by in Chem 2. So I'm going to look at this 1.10 something, 1.10. There's my 4 digits right there. And then this 7 would round that up. So 1.104. And then, yes, you must write it in proper scientific notation. You may not leave the E in there. That's a calculator issue, not really a correct notation. And then I would write atoms, because that's our unit. And then I would give it a label, atoms of lithium. So again, that's one of the ways that we would use this. I got one more problem, and then I think we're done with this particular example. So here's another example of the way we can use the mole and molar mass, kind of going the other direction. How much would 4.66 times 10 to the 25th atoms of gold weigh? So this is a great opportunity for you to hit pause and set this up and see if you can figure out how to work it out. And I'm going to kind of work it out on my screen. But if you can, hit pause. See if you can kind of work your way through that line of logic, following the units in your conversions and using those units to get to the unit that you want. So we're starting with atoms and we're getting to grams. So again, I'm going to set mine up. But you should hit pause and try this. You slackers, right? So atoms of gold. AU is the symbol for gold. There we go. Oh, I'm not going to have enough room. Crud. So tracing the units. I've got atoms here. So that means atoms has to go here. And then I can only convert atoms to one thing. You can always convert atoms to moles. This is Avogadro's number. Whenever we've got an item here, that's going to be Avogadro's number in the spot. So 6.022 times 10 to the 23rd atoms equals 1 mole. Okay, I still need to get to grams, and I'm not there yet, so I've got to do one more step. So I'm going to cross my moles down to the bottom, MOL. I know the abbreviation for moles is MOL. Thanks for saving me the E. And now I can convert from moles to grams. This step is a molar mass step. Whenever you do moles to grams, that's a molar mass step. So 1 mole equals some number of grams. And now this is gold, AU. So now I've got to get my periodic table out and find gold. Gold is located down here. And I can see from that the molar mass of gold is 196. It's heavy. 196.97. Again, with molar mass, our convention is we will use 2 decimal places all the times when we are doing molar masses. So our units cancel out. Atoms are gone. Moles are gone. Our final unit here is grams of gold. So now I can just calculate it again, multiply across the top, divide by the numbers on the bottom, 4.66 times 10 to the 25th times 196.97 divided by 6.022 times 10 to the 23rd. It's a long number, and I get a number. There it is, 15 something or other. It is 15242.11558 and change, whatever else is on there. So again, sig figs, units, and labels every single time. So if I take a look at my original problem has 3 sig figs, SF. So my 3 sig figs are right here. So now I can write this as 152, and then I can replace these by placeholder zeros. 00 works. That's what placeholders are called, placeholders. And I can just do grams of AU. That works. I can also write it in scientific notation, times 10 to the 1, 2, 3, 4, times 10 to the 4th grams of AU. You could also write it in kilograms if you wanted to. Just divide by 1,000 if you want. But again, this is how we use molar mass conversions, and Avogadro's number in some initial basic calculations. All right, there you go. I will see you in the next one where we will do this with compounds. All right, have a good one. I'll see you in a bit.